Hello everyone, welcome to the third video lesson for Chapter 7 of the Foundations of Scalable Systems. In this lesson we're going to delve into the world of messaging patterns and highlight three which are particularly pertinent to scalable available systems. With a long history of usage in enterprise systems, a comprehensive catalogue of design patterns exists for applications that utilize messaging systems. While many of these are concerned with best design practices for ease of construction and modification of systems and message security, a number apply directly to scalability in distributed systems. In the following slides, I'll explain three of the most commonly utilized patterns. If you need more, then the book here, Enterprise Integration Patterns, is a fantastic resource to draw on. A really common requirement for messaging systems is to consume messages from a queue as quickly as possible. With the competing consumers pattern, this is achieved by running multiple consumer threads and/or processors that concurrently process messages. This enables an application to scale out message processing by horizontally scaling the consumers as needed. The general design is shown here on the slide. Using this pattern, messages can be distributed across consumers dynamically, either using the push or pull model. Using the push approach, the broker is responsible for choosing an appropriate consumer to deliver the message to. A common method, which for example is implemented in RabbitMQ and ActiveMQ, is a simple round-robin distribution algorithm. This ensures an even distribution of messages to consumers. With the pull approach, consumers simply consume messages as quickly as they can process them. Assuming a multi-thread consumer, if one consumer is running on an 8-core node and another on a 2-core node, we'd expect the former would process approximately 4 times the amount of messages as the latter. Hence, load balancing naturally occurs with the pull approach. So overall, there are several advantages to this pattern, namely availability. If one consumer fails, the system remains available, and its share of messages is simply distributed to the other competing consumers. Failure handling. If a consumer fails, unacknowledged messages are just redelivered to the queue and then redelivered to another consumer. We also get dynamic load balancing. New consumers can be started under periods of high load and stopped when the load is reduced, without the need to change any queue or consumer configurations. You'll find support for the competing consumers in any production quality messaging platform. It's a powerful way to scale out message processing from a single queue. The competing consumers pattern throws out some implications that we have to deal with, and we can apply different messaging patterns to deal with these implications. The first one is message ordering. We can't guarantee that the messages delivered to consumers will be processed in the order that they are delivered to the queue. A message may be delivered to a consumer, however it may be delayed in processing it, and while it's delayed, many other messages may be processed by other consumers. So the competing consumers problem has to be oblivious to the need for messages to be processed in the order in which they are delivered to the queue. Also, how do we handle poison messages? Poison messages are messages that cause consumers to fail. I'll come back to this one in a second. Also, how do we handle idempotent message processing? This means that if a message is received by a consumer but then it fails for some reason, how do we guarantee that the message, when it's reprocessed, doesn't actually lead to duplicate message processing and give us some incorrect states in our application? Let's look at idempotence first. I delved into the issue of idempotence in Chapter 3 of the Foundations of Scalable Systems and the associated video lessons. Basically, transient network failures and delayed responses can cause a client to resend a message. This can potentially lead to duplicate messages being received by a server. To alleviate this issue, we need to put in place measures to ensure idempotent once-only processing. In asynchronous messaging systems, there are 2 sources of duplicate messages. The first is duplicates from the producer, and the second is the consumer processing a message more than once. Both need to be addressed to ensure exactly one's processing of every message. The publisher part of the problem originates from a publisher retrying a message when it does not receive an acknowledgement from the message broker. If the original message was received and the acknowledgement was lost or delayed, this may lead to duplicate messages on the queue. Fortunately, some message brokers provide support for duplicate message detection, and this ensures duplicates do not get published to a queue. For example, ActiveMQ's Artemis release can remove duplicates that are sent from a publisher to a broker. The approach is based on the solution I described in Chapter 3 of the Foundations of Scalable Systems, using client-generated unique idempotency keys for each message. Publishers simply need to set a specific message property to a unique value, as shown in the code on the example here. Here we have the unique key which we associate with the message as when we send it. On the consumer side, duplicates occur when the broker delivers a message to a consumer which processes it and then fails to send an acknowledgement. Maybe the consumer crashes or the network loses the acknowledgement. The broker therefore redelivers the message, potentially to a different consumer if the application is using the competing consumers pattern. It's therefore the obligation of consumers to guard against duplicate processing. Again, the mechanisms I described in Chapter 3, namely maintaining a cache or database of idempotency keys for messages that we've already seen and have processed, works fine. Many brokers will set a message header that indicates if a message is a redelivery. This can be used in consumer implementations of idempotence. It doesn't guarantee a consumer has seen the message already. It just tells you that the broker has delivered it before and the message remains unacknowledged. And finally, poison messages. These are a good one. Sometimes messages delivered to consumers just can't be processed. There's numerous possible reasons for this. Perhaps most common are errors in producers that send messages that cannot be handled by clients. This could be for reasons such as malformed JSON payloads or some unanticipated state change. For example, a student ID field in a message for a student who has actually dropped out from the institution and is no longer active in the database. Regardless of the reason, these poison messages have one of two effects. They cause the consumer to crash. This is the worst probability. The most common in systems that are under development and test. Sometimes though, these issues sneak into production. Bugs appear in production, believe it or not. And this causes failing consumers to continually cause operational problems because every time a poison message is delivered, a consumer crashes. The other implication is that you may handle the message correctly, but just not be able to process it. This causes the consumer to reject the message, as it's simply not able to successfully interpret and utilize the payload. In either scenario, assuming consumer acknowledgements are required for messages, the message remains on the queue in an unacknowledged state. After some broker-specific mechanism, typically a timeout or a negative acknowledgement, the poison message will be delivered to another consumer for processing with predictable, undesirable results. So, if poison messages are not somehow detected by your system, they can be delivered indefinitely. This at best takes up processing capacity and hence reduces system throughput. At worst, it can bring down a system and bring it to its knees by crashing consumers every time a poison message is received. Luckily, the solution is quite straightforward. Basically, you limit poison message handling to a specific number of times for a message to be redelivered. When this redelivery limit is reached, the message is automatically moved to a queue where problematic requests are collected. This is traditionally and rather macabrely known as the dead letter queue. As you probably expect by now, the exact mechanism for implementing poison message handling varies across messaging platforms. For example, the Amazon Simple Queue Service, SQS, defines a policy that specifies the dead letter queue that is associated with an application-defined queue. The policy also states how many redeliveries a message should be, after which a message should be automatically moved from the application queue to the dead letter queue. This value is known as the max receive count. In SQS, each message has a receive count attribute, which is incremented when a message is not successfully processed by a consumer. When the receive count exceeds the defined max receive count for a queue, SQS simply moves the message to the dead letter queue. Sensible values for redelivery obviously vary with application and characteristics, but a common range is like 3 to 5. The final part of poison message handling is diagnosing the cause for messages being redirected to the dead letter queue. First, you need to set some form of monitoring alert that sends a notification to engineers that a message has failed processing. At that stage, diagnosis will comprise examining logs for exceptions that cause processing to fail and analyzing the message contents in the dead letter queue to identify producer or consumer issues. And that wraps up the coverage of asynchronous messaging systems in the Foundations of Scalable Systems, Chapter 7. Next, we're going to start looking at serverless processing platforms, which are another very useful mechanism to enable you to scale your system processing. Thanks for watching.